So far, we talked about how you can calculate the WP for a program with variable assignments, if conditionals, and also sequential composition, so that we can actually prove any programs with such complexity about its correctness. We're going to introduce a final construct into the program, which is about loops. So loop, as you know, is a very powerful way to really calculate for computation by making successive approximation. You want to do one step, one little progress at a time for each iteration. And then one example which I'm going to use is about how you can calculate the maximum of from an array. We'll use that as an illustrating example. And the loops are very powerful. However, you got to be careful with what kind of errors you might make on your loops. Okay, so infinite loops is very likely if you, for example, you forgot to really increment your loop counter. In that case, termination will be an issue. Remember, if without termination, your program can only be shown to be partially correct. So all the other issues I'm going to mention in the list will be about partial correctness issue. For example, maybe off by 1, maybe your loop counter simply was not used properly. And also, if you got some improper handling of the borderline cases in whatever kind, that's also partial correctness issue. And also, you may not, let's say after your loop terminates, and then the post condition that you really desire to really establish was not established. That's also a very severe error you can make about the loops. Okay, so this is actually one example from your textbook. So on page 381 in the OOSC2 textbook, so these are 4 versions of the binary search program that have been published, but somehow they're all wrong. So the main point is having loops, even for a simple problem like a binary search, is already very hard to get right, even for a solution that's already published to the community. All right, so that's about just some motivating scenario for why we want to use loops. But for you, you definitely know how useful loops can be, but we want to get it right. Some very quick clarification about the syntax. So up to this point, you should really know about the from until syntax in the language we're using, IFO. So you got some initialization, you got some Boolean condition, and also you got some body of the loop, right, for each iteration. I want you to see the correspondence between this loop over here in another flavor of the loop that's in the C family language, like let's say a while loop. The only difference is you can see we got initialization, also we got the body of the loop and body of the loop. So these are just the same. Also you got precondition for the loop to start and also the post condition for the loop to terminate and establish. They are the same. So now the condition over here, you want to be careful, right? We already explained this when we spoke about the state design pattern for the very first design attempt. You may want to review that quickly for yourself. Okay, so this part here is really about the so-called exit condition, right? Let's compare them side by side. In the case of the B, as soon as B is actually satisfied, we're going to exit from the loop. On the other hand, the B over here, the entire expression over here is really about as long as this condition here is really true, we're gonna stay in the loop and keep executing the body of the loop. So if you think about whenever you got a loop like this in IFO, how can you translate it into a semantically equivalent loop in other language? All you gotta do is simply just negates the state, this exit condition over here. So rather than saying as long as rather than saying as soon as we actually reach B, we're going to exit from the loop. You can say as long as B is actually false, in that case, we're going to stay in the loop. So they are semantically equivalent, right? That's something I'd like to show, want to clarify first. But for the rest of the lecture, when we talk about loop correctness, we're going to focus on this particular style of the loop. But meaning-wise, it's really the same as this particular one, right? And vice versa. If you want to prove something about, if you simply got B over here, you will simply put not B over here, right? They are basically the exact logical opposition to each other. So let's now talk about what contracts you can write for a loop. So there are 2 constructs we're going to introduce. So after the initialization, you want to put something called looping variance, which is a Boolean expression. I will elaborate on what looping variance really means in the next slide. And after invariance, and one thing you can think about, the reason that you put invariance right after the initialization part, that means you want to check the invariance right away to see if the invariant has been established even before the first iteration. That's a very important rule to really remember when you check the looping variance. and also exit condition, and then we got the body of the loop. And at the end of the loop, we're going to put the variance over here. And the variance is not a Boolean expression. Typically, it should be some integer expression. Okay, so think about invariance should be some Boolean expression that you expect it to be always true. Otherwise, you're going to get loop invariant violation. And then for the variance, it's going to be some integer expression that you will expect that to be always larger than or equal to 0. As soon as it falls below 0 becomes negative, you're going to get variance violation. Okay, let's go a little bit more details about their definition in a single slide, just to summarize. So you want to use the loop invariance and variance to write the contract for your loops. For the loop invariant, it's a Boolean expression for partial correctness, meaning that you don't really use the loop invariant to argue about termination of your loops. Okay, you don't do that, just for the partial correctness. And then, as far as the course is concerned, the best way for you to think about what a loop invariant should be, you want to refer to the corresponding post condition. And then typically the loop invariant will just be a special case for the post condition. Let's see one example conceptually, and then we'll see in detail a little bit later. So let's say the post condition is, let's say you want to find out the maximum of the array. So the return value result is simply the maximum of the array. That's a post condition. So what about the loop invariance? Think about a loop invariant. Think about how you're going to run the loop. You're going to run the loop from left to right, and you want to scan through the loop one element at a time. So you want to make sure for all the elements you have scanned so far, and the current value of the result is really the maximum of the scan area so far. So that's the loop invariance. So you can see the result, which might still be subject to changes once you run more iteration. It is the maximum of the part of the array scanned so far. Let's say you scan from left to right, right? I'm going to visualize this for you maybe a little bit later, but for now, just get a concept. The loop invariant being a special case for the post condition. Okay, it should be, number one, established right before the very first iteration, and also at the end of each iteration, at the end of the first, at the end of the second, at the end of the third, etc. It should be maintained. Okay, just remember the timings of checking the loop invariance. Okay, let's talk about variance. The variance is really meant for proving termination, not for partial correctness. The variance is nothing to do with the post condition. The variance is only for proving about termination. So it's going to denote the number of iterations remaining. Think about, you may just start the variance expression being 10, and then its value should be strictly decreased by certain number, and then eventually you will get to 0, meaning that you have no more iterations to go through. Okay, so that's the most intuitive definition for variance. And then it will be decreased strictly. So the variance cannot really maintain to be the same value between iteration. It must be strictly decreased. And should be maintained non-negative, larger than or equal to 0. And then as soon as the loop variance reaches 0, that means the number of iterations remaining will be 0. That means no more iterations to go. You must exit from the loop. Otherwise, you will actually get into loop variance violation. Okay, so now again, let me emphasize, we talked about total correctness before. It's about partial correctness, in which case we're going to use the loop invariance to really prove it. Okay, it's about the partial correctness. And then for termination, we're going to use the variance, right? You want to know, first of all, the roles that each contract actually plays for the correctness of the loop. Okay, so this will be the flow chart for informing you about how the contract of a loop should be checked at runtime. Let me just emphasize that. We already spoke about how it should be checked at runtime. Let's just be more explicit. Number one, you want to think about loop invariance. If you look at the loop invariant over here, it's simply just I over here, right? And also we got our loop variance about termination. It's the V over here. Let's just go through the timing of checking them. Let's talk about loop invariant first, which would be I, right? First of all, I is going to be checked right after the initialization and before you actually will go into the body of the loop, right? Before you go in there, right? But if the loop invariant is not satisfied, in that case, you're going to get loop invariant violation. Okay, so that'll be the first timing of checking the loop invariance. And then at the end of each loop, since we'll simply just go back to this particular part, which will be checking the loop invariant again. So that means at the end of each loop, you also check the loop invariance. If it is not satisfied, you're going to get loop invariant violation. Okay, so that's about the timings of checking a loop invariance. What about variance? For the variance, it will simply just at the end of each loop, you will simply check to see whether the variance is actually non-negative, larger than or equal to 0. If it is actually satisfying this constraint over here, of course, you will just go back to the beginning of your loop. Otherwise, you're going to get loop variance violation. Okay, so now you really want to know very clearly, before we see the example, about the timings of checking looping variance versus loop variance. The simplest example I can think of to really show you is this particular one. Okay, I will leave you to study the details of this particular loops. It's actually a very easy loop. We'll simply go from a particular value, and then we got invariance, we got exit condition. As soon as I is strictly larger than 5, we're going to exit from the loop. And then we're simply just going to print out this string value from every iteration. And then we got a variant over here. Okay, you may want to pause the video and just to make sure you know exactly how this loop works. And then think about what will be the console output from this particular loop. All right, so assuming that you have thought about it, so let's see exactly what's going to happen. So what will be the console output over here? So we're going to get iteration. Okay, every time it's going to be iteration as a prefix, and then I'm just going to omit that just for simplicity. Right, it's going to be i.out. For the very first iteration, it's going to be starting from 1. Iteration 1, 2, 3, 4, and 5, right? When I is equal to 5 for the first iteration, we're going to print out iteration 5. However, after this, we're going to increment I to be of value 6. So you should think about the 6 is really the final value for I. Because as soon as this becomes 6, it's going to be strictly larger than 5. That means we're going to exit from the loop. But 6 is never output to the console, right? 6 is really the value for I that you know that is going to satisfy the exit condition, right? So this is not output. But I'll just put it there just for you to see, right? However, when you check the looping variance and invariance, you have loop invariant and variant, you have to use also the value 6 because it's actually there. So now let's think about how you may check the looping variance. First of all, we know that the first timing will be you want to check the looping variant right after the initialization. So when I is simply equal to 1, so it's 1 between 1 and 6, indeed. So this checks. That's okay. And then at the end of each loop, you can think about at the end of loop number 1, we're going to get I is equal to simply equal to 2, right? Because you can think about after printing 1, I will be incremented to 2. So 2, 3, 4, 5, and the final value to check will be 6. So for all 5 values over here, 2, 3, 4, 5, 6. So these values will be checked for invariant satisfaction. So now, all of them are simply within this particular range between 1 and 6. So all of them will simply just check, right? So at the end of, again, at the end of the first iteration, I will be checked when it is equal to 2. At the end of the second iteration, I will be checked when its value is actually equal to 3, and etc. For the final iteration, I will be checked when its value is simply equal to 6. In that case, it will still satisfy the invariance. What about loop variance? For the loop variance, at the end of the first iteration, we're going to check to see i's value being 2. So now, if you try that, it's going to be, for example, 6 minus 2. So that'll be the first time, right? At the end of the first iteration. 6 minus 2, it will be 4, which is larger than or equal to 0. That's okay, right? Also, 6 minus 3 at the end of the second iteration. That's going to be 3, also larger than or equal to 0, and etc. What about the final iteration? For the final iteration, it's going to be 6 minus 6, right? Right after I has been incremented from 5 to 6. So now, after this, 6 minus 6 will just be 0. It will still be larger than or equal to 0. That means the remaining number of iterations left will be simply just 0. So we are done. So this is actually the simplest example I can think of just to show you. So the looping variance is actually correct over here. The looping variance is simply correct. You will not run into any looping variant violation. And also for the variance is also correct. You will never calculate its value that's below 0. Okay. One more intuition you want to gain about the loop variance. Think about what's going to happen here. If you think about, let's say, iteration, and the loop variant value, right? You can see at the end of the first iteration, it's going to be 4, and then 3, and all the way to 0. So you can think about 1, 2, 3, 4, at the end of the 1, 2, 3, 4, 5. At the end of the first iteration, you're going to get 4 over here. At the end of the second iteration, you're going to get 3, and then 2, and then 1, and then finally you will get into 0. So you can think about it strictly decreasing like this. And then as soon as you get to this point over here, so this is at the end of the 5th iteration. Okay, 1, 2, 3, 4, 5, right? At the end of the 5th iteration, the root variant value is simply equal to 0. That means it's about time to exit. If you're not ready to exit, you're going to get into a variance violation. All right, so hopefully that's good enough for you. So let me just give you a little bit of challenge over here. Challenge number 1. Let's say we modify the invariant to be this one here. So now rather than less than or equal to 6, I'm going to say less than or equal to 5. So now do you see any potential violation of the invariance? Okay, hopefully you can see that. You can pause the video and think about it. But let's see this. You can see at the end of the last iteration, we're going to, after outputting 5 for I, we're going to increment I into 6. So that means at the end of the 5th iteration, you're going to check to see 1 less than, okay, let me put it here. At the end of the 5th iteration, I would have been increased to 6. So that means 1 less than or equal to I less than or equal to 5, right? That's a modified invariance. And now it will just be 6. Apparently, it's going to be loop invariance violation. It's simply false. Okay, hopefully this small modification can show you that just by changing the loop invariance, you might run into violation. Okay, another one. What about this? Let's say the loop invariant, we change it back to the correct one. Let's say the variance, we simply change that to be, rather than 6 minus I, it will be 5 minus I. Okay, so let's see, are you going to run into any loop variant violation? Pause the video and think about it. All right, assuming that I thought about it, again, you can see at the end of the last iteration, we know that I's value will be incremented to 6. So that means when we try to check to see whether the loop variance will be satisfied, we're going to get this. At the end of the 5th iteration, so the loop variance will be basically 5 minus 6, which is equal to minus 1. And now, larger than or equal to 0 is simply equivalent to false, right? That's always the property we want to check about the loop variance being non-negative. Okay, so that means we're going to get loop variance violation. All right, so really try to look at these two hypothetical changes about loop invariance and loop variant and see why the corresponding contract violation can occur. All right, so let's now summarize all the Boolean conditions you should be concerned about when you are trying to check the contract for a loop using this diagram over here. Okay, remember we talk about every Boolean condition or predicates is simply a set of satisfying values for that particular condition. So now let's look at this particular area as the loop invariance. So this is one particular set, right? So you can see so you can think about as soon as we initialize the loop, we are going to get into this initial states before we enter the first iteration. You can think about once we execute the body of the loop, this will be the first iteration. And then at the end of the first iteration, the states must be within the region of the loop invariant, meaning that we are still maintaining the loop invariant and etc. Right? You can have as many iterations as you like. So this will be at the end of the second iteration. End of, and this one will be the end of the first iteration. All right? And then eventually you're hoping that you'll be reaching the states over here. So this particular states is at the end of the final iteration. The final iteration. And that particular state you can see is a member of basically 3 sets. Let's now be very careful to really circle them. Number 1 is going to be satisfying the loop invariance over here. You can see that final state, right? You can see it's a member of the blue one. And also, it's now time to exit, which means the exit condition should also be satisfied over here. And most importantly, the post condition upon termination of the loop should also be established. So this is why this is also satisfying the post condition. You can think about that's the outcome from the loop. And notice that this state is also in the intersection between the looping variance and also the post condition. This is why we said as far as this part of the course is concerned, you only have to worry about the looping variance where the looping variance is simply a special case for the post condition. We'll see another example in just a moment. All right, so now that's about the syntax and some simple example for the contract for the loop. In the next video, we'll speak about a slightly more complicated example for looping variance and loop variance.